Okay, good morning. Welcome to this class. Today we're going to have a look at the first lesson of chapter 4, the derivatives of sine and cosine functions. Remember that in our previous lessons, we have talked about the differentiation rules, such as the sum and difference rules and product and quotient rules, as well as the chain rule and implicit differentiation method, right? And also we talked about the derivatives of some of the elementary functions, for example, the power function and the polynomial functions, right? So from today on, we're going to have a look at the derivatives of some other elementary functions. For example, the sine and cosine functions, exponential functions, and logarithmic functions. So today it's our very first lesson of chapter 4. We're going to have a look at the derivatives of the sine and cosine functions. Okay, first of all, let's have a look at the learning goals. After this lesson, you are expected to be able to obtain the differentiation rules for sine and cosine functions using the first principle definition. Then use the differentiation rules for sine and cosine function to solve related problems. Okay, so first, let's have a look at the derivative of the sine function. Again, we can apply the first principle's definition of a derivative to find the derivative of y equals sine x. So suppose we have our original function y equals sine x, then the derivative of this function by definition is given by dy by dx, which is defined as the limit as h approaches 0 of sine x plus h minus sine x over h, right? Then we can expand sine x plus h to sine x cosine h plus cosine x sine h, then minus sine x over h, right? Then we can put the common factor sine x in front, and what's left in the parentheses are cosine h minus 1. Then the second term is cosine x sine h, right? Then this can be rewritten as the limit of h approaches 0 of the sum of two expressions. First expression is sine x times cosine h minus 1 over h, and the second expression is cosine x sine h over h, right? Remember, according to the limit rules, this can be divided to the sum of two limits, right? The limit of two expressions equals the sum of the limit of the two expressions. So that equals the limit of the first expression plus the limit of the second expression as h approaches 0, right? And note here for the first expression, sine x has nothing to do with h approaches 0, right? So we can treat sine x as a coefficient constant. So we can put it in front. That gives us sine x times the limit of h approaches 0 of cosine h minus 1 over h, right? The second expression is, again, we can put cosine x in front. Then that is limit of sine h over h as h approaches 0, right? Okay, so next you need to evaluate the limit of this expression as h approaches 0 and the limit of the second expression sine h over h as h approaches 0, right? Okay, so next let's have a look at how we can find the limit of these two expressions. But before that, I'll give you some time to have a look at the process here. Can you follow me here? Do you have any questions? Any questions? Okay, if you have no questions, let's have a look at how we can evaluate the limit of such two expressions. So first, let's have a look at the limit of sine h over h as h approaches 0, okay? Okay, first, let's find the limit of sine h over h as h approaches 0. We can consider this problem in a unit circle. So first of all, let's draw a unit circle. Unit circle means a center is at its origin point, O, with radius of 1, right? Then let's consider a angle h. So h here is an angle, okay? So we need to consider when h approaches 0, the limit of sine h over h, right? So when h is approaching 0, that has two possibilities. So first, let's consider if h approaches 0 from the positive side. That means h must be a very small angle in the first quadrant, right? Which is very nearing 0 here. So let's zoom it a little bit. So suppose h is here. Then we need to consider what is sine h. Okay, suppose the intersection point between the terminal arm of h and the unit circle is marked as point A. And then let's draw a perpendicular line AB such that B is a point of intersection between AB and the x-axis. Then we know that sine h is actually AB over the radius of the unit circle, which is 1, right? Therefore, sine h is actually the absolute value of the section AB, right? Can you follow me? Because that's that's the definition of sine h, sine alpha, right? On the other hand, you need to consider what is h. So h is a angle in radians measure, right? In radian measure. Therefore, according to the definition of radian measure, h is defined as the ratio between the length of the arc, which is the length of AC, which is arc AC, over the radius r, which is 1 here, right? Therefore, we know h should equal the length of the arc AC. This is very important. Can you see why? Because it's just the definition of the radian measure, right? Radian measure of h is defined as the length of AC over the corresponding r, which means the absolute value of the length AC, right? Okay, so the limit of sine h over h as h approaches 0 is actually equivalent to or equal to the length of AB, which is the length of this section, over the length of the arc AC, which is the length of the arc highlighted in green here, right? So as you can imagine, when h approaches 0 from the positive side, that means h is a very small angle. For example, could be here, right? When h is very small, we can imagine that these two lengths are actually equal to each other, right? As h becomes smaller and smaller and smaller and smaller, that is close to the 0, which means the terminal arm of h is approaching the positive side of the x-axis, right? Can you imagine that? AB, the length of AB and the length of arc AC are actually equal to each other, right? So the limit of this ratio should equal 1 as h approaches 0 from the positive side. You see that? Okay, so that solves part of the question. When h approaches 0 from the positive side, this limit equals 1, right? Okay, then we can consider the other half of this question. When h approaches 0 from the negative infinity, that means h is here. It's a very small angle in the fourth quadrant, right? Then sine h is actually, so now or A is here, right? B is here. So sine h is actually a negative number, which is negative the length of section AB. Similarly, angle h in radian measure is, according to the definition, is also a negative number, which is negative the length of arc AC, right? Which is this length. So here, similarly, this should be approaching 0 from the negative side. All right, there's a typo here. Let's correct this. Okay, therefore, the limit of sine h over h as h approaches 0 from the negative side, that equals negative the length of AB over negative the length of arc AC, which also equals AB over the arc AC, which is also 1, right? Also, let's correct this a little bit. There should be a limit symbol here. As h approaches positive. So here also we should have a limit symbol. Do not forget that. Okay. Okay, so that means when h approaches 0 from the negative side, the limit is also 1, right? If you have an expression and when h approaches 0 from both sides equal the same number, that means when h approaches 0, the limit of this expression should equal 1. You understand? Can you follow me? Okay, so this means we have successfully evaluated the limit here, which is actually 1, right? That solves the second part of this equation. Then let's consider another limit here, the limit of cosine h minus 1 over h when h approaches 0. Well, we can actually solve this limit in this way. So note that cosine h minus 1 over h equals cosine 2 times h over 2 minus 1 over h, right? And then we can expand this expression using the double angle formula. This gives us 1 minus 2 times sine of h over 2 squared minus 1 over h, which is simplified to negative sine h over 2 squared. And also note, h can be rewritten as 2 times h over 2, right? So again, here, we can cancel a common factor 2, which gives us negative sine half of h squared over h over 2, right? So the limit of cosine h minus 1 over h as h approaches 0 can be rewritten as the limit of negative sine half h squared over half h when h approaches 0. So when h approaches 0, this is actually equivalent to 1/2 of h approaches 0, right? Because we have when h approaches 0, half of h must approach 0, right? Also, when half of h approaches 0, we also have h approaches 0. These two expressions can imply to the other one with each other, right? So we can actually rewritten the limit as this expression here. The original limit here is actually the limit of negative sine half of h square over half of h as half of h approaches 0, right? Okay, so we can let half of h equals u, right? So this limit is actually the limit of negative sine u square over u as u approaches 0, right? Okay, so this problem is really the limit of sine u times negative sine u then over u when u approaches 0, right? Then we can rewritten this expression as limit of as u approaches 0 sine u over u, that's the first part, times negative sine u. Also, according to the limit properties, the limit of the product of two expressions equals the product of the two limits, right? So that can be rewritten as the limit of sine u over u as u approaches 0 times the second limit, which is the limit of negative sine u as u approaches 0, right? Okay, so what is the first part? What is first part here? We have already evaluated this limit, right? So pay attention here. The limit of sine something over something. This is the same radians, same angle in radian measure, right? Limit of sine h over h as h approaches 0. Also, you can use the letter u, right? So that means the limit of sine u over u as u approaches 0 is 1 here, right? Then that's actually equals 1 times the second part, which is the limit of negative sine u as u approaches 0. So we can imagine that when u approaches 0, which is an angle that is very close to the positive side of x, right? In this case, the limit of negative sine u should equal 0, right? So the limit of this expression is finally simplified to 1 times 0, which is actually 0, right? Okay, so let's get back to the expression here. We have proved that this limit is actually 0. So that gives us sine x times 0 plus cosine x. So what does this mean? This means the derivative of the sine function is actually cosine x, right? So finally, dy by dx is actually cosine x. This is a derivative of a sine function. Understand? Okay, so let's make a summary here. If y equals x, if y equals sine x, dy by dx equals the sum of the limits of these two expressions. And then we can prove that the second part is cosine x times 1. The first part is sine x times 0, right? Then the derivative of y equals sine x is actually cosine x. Therefore, we have this conclusion. d sine x by dx equals cosine x, or the derivative of sine x equals cosine x. You understand? Okay, I'll give you some time to have a look at the whole process here. This is why we can obtain the derivative of sine x. All right, if you don't have any questions, now consider this question. So now we know how to get the derivative of y equals sine x, right? Suppose we have a function y equals cosine x. Can you find dy by dx? Okay, I'll give you 5 minutes to think about this question. Can you obtain the derivative of cosine x using what we have learned so far? Okay, have you finished? Any ideas? Okay, so here we have already know the derivative of the sine function, right? So in order to get the derivative of the cosine function, you need to convert cosine to sine according to the trigonometric properties, right? Okay, so note that cosine x can be expressed as sine of half pi minus x, right? Therefore, we know dy by dx is actually d of derivative of sine half pi minus x by dx, right? So basically, we're going to find the derivative of sine half pi minus x, right? And then we can use the chain rule to find the derivative of a sine function. So outer function is sine u, right? Which is cosine u, according to what we have got here. Derivative of sine u equals cosine u, right? And inner function is half pi minus x. So the derivative of the inner function with respect to x is just -1, right? And this gives us, so note here, cosine half pi minus x, according to the trigonometric cofunction identity, this is sine x, right? Sine x times -1 equals negative sine x. So the derivative of cosine x equals negative sine x. Can you follow me? Okay, so let's make a summary here. If y equals cosine x, then the derivative of cosine x, which can be expressed as dy by dx, or the derivative of cosine x, equals sine of half pi minus x, the derivative of sine of half pi minus x, and this can be evaluated as negative sine x. Therefore, we have the following expression. Derivative of cosine x with respect to x equals negative sine x. Okay, any questions? Okay, I'll give you 2 minutes to have a look at the solution here. All right, if you don't have any question, let's take a 10 minutes break. After that, we'll use these two derivatives of sine x and cosine x to solve some of the typical questions. Okay, please return before 10 o'clock. All right, welcome back. So next, let's have a look at some example questions. First, let's have a look at this question here. Find each derivative with respect to x. First, y equals 2 times sine x. Question B, fx equals -3 cosine x. Okay, I'll give you 2 minutes to have a look at this question. Try to solve this by yourself, okay? Can you find the derivatives of these functions with respect to x? Okay, have we finished? Okay, so we can solve the derivatives of these questions using what we have just learned, right? The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x, right? Okay, so first question, dy by dx equals 2 times cosine x. So we can apply the constant multiple rule to put the constant in front, and then find the derivative of sine x with respect to x, which is cosine x, right? Second question again applies the constant multiple rule that gives us -3 times the derivative of cosine x, which is negative sine x, and that gives us 3 times sine x. Any questions? Okay, if you have no questions, let's look at some more practices. So how about these two questions? Differentiate with respect to x. A, y equals sine x plus cosine x. B, y equals 2 cosine x minus 4 times sine x. Okay, again, I'll give you 2 minutes to have a look at these questions. Okay, have we finished? Then let's have a look at the solution. First question, we can apply the sum rule, right? The derivative of the sum of its two expressions equals derivative of the first function plus the derivative of the second function, which equals cosine x plus negative sine x, which equals cosine x minus sine x, right? Any questions? Then for the second question, we can apply the difference rule and constant multiple rules. The derivative of this composite function equals negative 2 sine x minus 4 cosine x. Okay, any questions? No? Okay. No questions. Let's have a look at another example. So find the slope of the tangent line to the graph f(x) equals 3 sine x at the point where x equals a quarter pi. Okay, this time I'll give you 5 minutes to have a look at the question here. All right, have you finished? Okay, let's have a look at the solution. To find the slope, differentiate the given function with respect to x, right? Then evaluate the derivative at x equals a quarter pi. Then we can find the slope at that point. Well, first of all, if fx equals 3 times x, 3 times sine x, then we know the first derivative of fx should equal 3 cosine x, right? Then we can evaluate the value of the derivative gives the slope of a tangent passing through the point on fx, where x equals a quarter pi. So when x equals a quarter pi, the slope, which is actually the first derivative at this point, equals 3 cosine a quarter pi, right? We know a quarter pi is a special angle, so we can evaluate cosine a quarter pi manually, which is actually 1 over square root of 2. So the derivative or the slope of the tangent line is 3 over square root of 2. Or you can also rationalize the denominator. This is 3 over 2 times square root of 2. So we can make the conclusion the slope or instantaneous rate of change when x equals a quarter pi is 3 over square root of 2, or 2 over 3 times square root of 2. Okay, any questions? Okay, I'll give you 2 minutes to have a look at the solution here. Okay, have you finished? If you have no questions, let's have a look at another practice. Okay, have a look at this question here. Find the equation of the tangent line to the curve fx equals -2 sine x at the point where x equals a fixed pi. Again, I'll give you 5 minutes to have a look at the question by yourself. Okay, have you finished? Okay, let's have a look at the solution together. First, we can calculate the point of tangency with x coordinate at x equals 6 pi, right? Well, we can insert x equals 6 pi, and then that gives us f of 6 pi equals -1, right? So the required tangent point is a 6 pi -1. We know the tangent line passes through this point. Next, we find the slope of the tangent line. We can first differentiate the function with respect to x to get the derivative of that function. So the derivative of fx equals -2 times cosine x, right? Then we evaluate the derivative at x equals 6 pi. This gives us negative square root of 3, right? So that means the tangent line passes through this point and with a slope of negative square root of 3. Then the point slope form of this tangent line is y minus y1 equals m times x minus x1. So x1, y1 is the point, it's a tangent point, right? It's the point on that line. And m is the slope of that line. So we insert these values in that equation. So that gives us y plus 1 equals negative square root of 3 times x minus 6 pi. Then we convert this line to the slope intercept form, which is y equals negative square root of 3 times x plus square root of 3 pi over 6 minus 1. Okay, any questions? I'll give you 2 minutes to have a look at the solution. Any questions, just let me know, okay? Okay, let's have a look at another example. Find the derivative with respect to x for each function below. Question A, y equals cosine 3x. So in order to avoid any ambiguity, it's better to put a parenthesis here. Second, fx equals 2 times sine pi x. Okay, I'll give you 5 minutes to have a look at these two questions here. All right, have you finished? Okay, we can have a look at these solution together. So note here, both of the functions are composite functions, right? So we need to use the chain rule to evaluate the derivative of these functions. Question A, y equals cosine 3x. The outer function is cosine u, right? Inner function is 3x. Therefore, dy by dx is dy by du, where u is 3x, times du by dx. Okay, so the derivative of the outer function is negative sine u. The inner function, derivative of the inner function is 3, right? Okay, so that gives us negative 3 times sine u. Note here, u is 3x. Therefore, the final solution is negative 3 times sine of 3x. So if you are already very familiar with this process, you can also directly write the derivative of such a function. So the derivative of cosine 3x, for example, you can directly write the derivative of the outer function, which is negative sine 3x, times the derivative of the inner function, which is a derivative of 3x with respect to x. Therefore, it is 3, right? So we can directly write the final result is negative 3 times sine of 3x. Okay, so if you're not very familiar with this method, you can slow down a little bit. Just let y equals cosine u and u equals 3x. You can choose either way, okay? And for the second question, again, the derivative of this function equals the derivative of the outer function, which is 2 times cosine pi x times the derivative of the inner function, which is pi x. The derivative of pi x with respect to x, of course, is pi, right? Therefore, the final solution is 2 pi times cosine of pi x, right? Okay, any questions? Okay, I'll give you 2 minutes to have a look at the solution here. Any questions, just let me know, okay? Okay, then let's have a look at another question. Differentiate with respect to x for each of the following equation functions. First question, y equals cosine x cubed. Next question, y equals 2 sine x cubed minus 4 cosine x squared. Okay, I'll give you 5 minutes to have a look at these two questions. Okay, so let's have a look at the solutions here. Question A, dy by dx is 3 times cosine x squared times negative sine x. So the final result should be negative 3 sine x times cosine x squared. Next, y equals 2 times sine x cubed minus 4 cosine x squared. dy by dx is given by 2 times 3 sine x squared times the derivative of the inner function, which is cosine x, minus 4 times 2 times cosine x times the derivative of the inner function, which is negative sine x. And final solution is 2 cosine x sine x times 3 sine x plus 4. Okay, any questions? Okay, if you have no questions, let's have a look at the last example of today's lesson. Find each derivative with respect to t. Okay, I'll give you 5 minutes to have a look at this question here. Okay, any questions? Let's have a look at the solution here. The derivative of the first function, dy by dt, is, first of all, we should use the product rules, right? The derivative of the first function, t cubed, times second function, cosine t, plus the first function, t cubed, times the derivative of the second function, the derivative of cosine t, which gives us 3t squared times cosine t minus t cubed times sine t. Okay, second, let's have a look at the derivative of ht, dt by dh. Again, we should use the product rules, which gives us the derivative of the first function times the second function plus the first function times the derivative of the second function. And this gives us the final result is 4 cosine t squared times cosine 4t minus 2 times sine t times cosine t times sine 4t. Okay, I'll give you 2 minutes to have a look at the solution here. Any questions, just let me know, okay? Okay, if you have no questions, let's give it a summary of today's lesson. Let's revisit today's learning goals. So after this lesson, now you should be able to obtain the differentiation rules for sine and cosine functions using the first principles definition, and also use the differentiation rules we obtained from the first step for sine and cosine functions to solve the related problems like the examples we have discussed. Okay? All right, so if you have no questions, please remember to complete today's homework and submit them on time to Google Classroom, okay? All right, if you don't have any questions, class dismissed for today.